Okay, so this week in our parent class, we're talking about the fundamental theorem of calculus, which has two parts to it. And we focus most of our attention on part two of that theorem because it really is the more important of those two parts for what we do in this class. However, part one, the type of problems that we deal with in part one can be a little bit confusing for students who are seeing it for the first time. So we're going to use the support class this week to practice working with the first part of the fundamental theorem of calculus. And basically what we're going to be doing here is part of what a complete problem would look like in that class. So I'm going to read the instructions and we're going to work through three examples of how this looks or how this works. Start by defining g of x to equal this integral, the integral from 0 to x of f of t dx. In the parent class, we talk about this integral, specifically that the input for this function is used as the upper limit of integration here. So this x assigns different upper limits of integration to this thing. We're not going to talk any more about that here because that's covered in the parent class, but that's how we're defining g of x for all of these problems. And then for each problem, we're going to do two things. There's an a and a b. So the first thing we're going to do is represent capital F of x, which will be defined in the problem, as a composite function or a sum or difference of composite functions involving this g right here. So that's part A. Part B, we're going to take the derivative of that function f, so f prime, in terms of g prime and x. It's this second part where we're applying the fundamental theorem of calculus. And the fundamental theorem of calculus is the one that basically says this. I'm going to put this off over here. If capital F of x is equal to the integral from some constant a to x of f of t dt, then capital F prime of x is equal to little f of x. Okay, and again, we talk about that in more depth in the parent class as well. This is a capital F. Let's make it look a little more like a capital. Okay, so the key thing that's going to come up in all of these problems is we're going to be defining capital F of x similar to this, but where the upper limit of integration is not just an x. It's going to be some function of x. It's g of x that's defined exactly this way. So we have to make little modifications to be able to apply this theorem, and that's what part A is setting up for us. So let's take a look at this first example. For this first one, we're going to define capital F of x to be the definite integral from 0 to 4x to the fifth power of f of t dt. Okay? Now, taking a look at the first thing we're supposed to do, we want to represent f of x as a composite function involving g, where this is what g is. Compare the way that we define g of x to f of x. They look almost identical. The only difference is that where g of x has an x in its upper limit of integration, capital F of x has a 4x to the fifth. So if I were to take this x out and replace it with a 4x to the fifth, I will have capital F of x. But that can be accomplished by plugging 4x to the fifth in for this x here, which would look like this. G of 4x to the fifth is what f of x is equal to. Okay? I think I probably would have wanted to write this the other way around, but that's fine. This works just fine. So that is the relationship between these two, and this one is a composite function. I took a function, 4x to the fifth, and plugged it into another function, g of x. That's all that there is to do for part A. Part B wants me to find f prime in terms of g prime and x. And really all this amounts to is if I'm going to take f prime of x, I'm taking the derivative of this, since that's what f of x is equal to. But this is a composite function, which means I have to use the chain rule to do that. So the chain rule says if you have a function composed with another function, you take the derivative of the outside function and leave the inside alone. So it looks like g prime of 4x to the fifth. And then we multiply that by the derivative of the inside function. 5 times 4 is 20. Subtract 1 from the exponent, and I get that. So that's what part B is. That's all there is to it. Okay, so again, part A looks at this upper limit of integration, and if it's different from just an x, we use it as a substitution in that x right there, forming a composite function. Then the part B, we differentiate that composite function using the chain rule. And that's the whole thing. Now, that's the simplest version of this type of problem. There are little things that we can do to complicate it a little bit. So what if I defined f of x to be equal to this? The integral from the natural log of x to 0 of f of t dt. Okay, once again, compare this to g of t, or g of x. So not only am I using a function of x as one of my limits of integration instead of just an x, but the limits of integration are also in the wrong places. So here I should have 0 as my lower limit and then x as my upper limit, whereas here 0 is my upper limit and the natural log function is showing up in my lower limit. So the way that we handle this is we use a I almost said a logarithm property, an integral property that allows us to switch these limits of integration as long as we multiply this by a negative. So if this is the case, then if I took negative f of x, that would equal the negative of this integral. But that negative can be used to switch the order of integration, and now there's no more negative f of t dt. Okay, so this thing is the opposite of this. If I multiply both sides of this by a negative, I can say that f of x is equal to negative 0 to the natural log of x, f of t dt. Okay, so at this point, I would want to compare this again to g. They look similar. If we just kind of ignore the negative for a second, the only difference between this function and the way I define g of x up there is that where I have a natural log function, I should be seeing an x instead. So I'm going to take my g of x function. This is part A. We have this negative here. But then we also have what looks like g of x if I plugged a natural log of x in for it. That's how I would define this one, negative g of the natural log of x. Part B, I take the derivative of that with respect to x. And once again, using the chain rule, we just get negative g prime of the natural log of x times the derivative of the natural log, which is just 1 over x, like that. Okay? So we have a couple of examples. I want to look at one more example. It's the most complicated type we're going to see. So this one, I'm going to set f of x equal to the integral from 6x minus 1 to 5e to the x. And then I have the same integrand, f of t dt. So for this one, I'm comparing this to g of x, and I can use the previous two examples as kind of inspiration for what to do. This one is a problem because I don't have a 0 showing up in either of my limits of integration. In the first example, I had a 0 and it was where it belonged. In the second example, I had a 0, but it was in the wrong place. I was able to get it in the right place with a negative. Here, there is no 0 at all. So what I'm going to do is I'm going to use a property of definite integrals, another property that allows you to split it into two definite integrals. This is the same thing as the integral from 0 to 5e to the x of f of t dt, plus the integral from 6x minus 1 to 0 of f of t dt. This is a property that we talked about in the section of the parent class where we introduced definite integrals. In that section, it says it uses an a and a b and then a b and a c. So the key is that this lower limit and this upper limit have to be the same thing. I chose 0 because I know that 0 shows up in my definition of g, which is what I want to use. But that 0 could have been any other number as long as this matches this. So I'm getting things that are close to being in the form that I want them to be, but I'm noticing that the second definite integral, the 0 is in the wrong place. So using the same, this is f of x here, using the same technique as the previous problem, I can switch the order of this of these limits of integration and just change this plus to a minus, which accounts for the negative that we need in order to do that. So now this is going to look like this. Minus okay, and that's f of x right there. So with that, I can do part A now. This first integral is what g of 5e to the x would look like, minus g of 6x minus 1. And this is why in the instructions up here it says represent capital F as a composite function or a sum or difference of composite functions. It's because in a case like this, we end up with a difference of composite functions. This is what f of x is equal to. Now we want to take a derivative. What is f prime of x? Well, once again, I'm taking the derivative of this. It's a difference of functions, so I can take the derivative of each one separately. But in each case, I need to use my chain rule. So this first one's going to look like g prime of 5e to the x. 5e to the x is its own derivative. So when I multiply by the derivative of the inside, it's going to look like this. Minus g prime of 6x minus 1 times the derivative of the function on the inside, which again, this is just 6 when I take its derivative, okay? And that's the answer for part B. So all of the problems on the assignment for this week in Maths 40 is going to look, or they're going to look like one of these 3 types of examples. There's only 6 problems total on the assignment. You get 2 of each type, basically. So this is basically what you're doing. Now, in the parent class, we go a little bit further than this. In the parent class, when we're dealing with the fundamental theorem of calculus part 1, instead of an f of t being shown here, you're going to have an actual function. So it'll say something like t squared plus 2t or something like that, whatever the function happens to be. And then once you get to this step for like part B, you're going to use the fundamental theorem of calculus to write g prime of this as just f of this. And then you use the function that's given to you. We do examples like that in the parent class, so we don't need to really explain that more here. But for the support class, this is as far as we are taking these types of problems. That's going to be it for this week.